So previously we looked at the IQR as a measure of spread for data. Next we have something called the standard deviation, which looks a little bit more arcane in how we calculate it, but it is not really that mysterious. Suppose we have these two data sets. Take a look at them for a second. 4, 5, 5, 5, 5, 5, 5, 5, 5, 5, 6, and 1, 2, 3, 4, 5, 5, 6, 7, 8, 9. I hope you can see that these data sets are both symmetric. Let's make a plot of them. Here's dataset x1 on the left. Most data points are 5, with one point that's less and one that's more. And here we have just 2 points that are 5 and even tails on both sides. So these data have the same center, but they are spread out in different ways, and we want a way to measure that. So how could we do that? Well, one thing we might do is first compare the means. I can see if I average 6 and 4, I get 5, 5 and 5, I get 5. The average is 5. The same for the second. So the only thing differing about these is how much they're spread out. So the thing we can ask is, what is the average deviation, or what is the average difference from each data point to the mean? Let's plot that. We'll make a little chart. I can see that my data here, if I take each data point minus the mean of that data set, 4 minus 5 is, 5 minus 4 is -1. I have a -1 and a +1, and the rest are 0 for this first data set because all of those values are equal to the mean of that data set. We have more spread in the second data set with data that are 4 less, 4 more than the mean. But what would happen if I added up this whole column and added up the total deviations from the mean? Well, I see I have a +1 and a -1. I get 0. And similarly here, these pairs all cancel out. 4 and -4, 3 and -3. So if I add up all the deviations, I'm going to have a problem. And in fact, that will always happen. That's what it means to be the mean. So you can see if you can prove that. That is not a requirement, but a fun challenge. See if you can prove that if you add up all the deviations from the mean in a data set, you're going to get 0. So we need another trick to measure some well-defined number that is a measure of how far out these are spread. I know I'd like those differences all to be positive. So you might be thinking absolute value, but that is not quite what we do. Instead, what we do is take the deviations of each data point minus x bar and square them. So we square all the deviations and add them up, and then we almost take the average, but we divide by n minus 1 instead of n. We'll talk about why that is. And that number, s squared, has a name. It's called the variance. And to calculate the standard deviation, we take the variance, which we can also write this way with our sigma notation more compactly, and we just take the square root of that number, and this is called the standard deviation. This is a measure of how far on average data points are from the mean, but how do we measure it? We measure the average squared distance and take the square root. One little wrinkle that we divide by n minus 1 rather than n, so that's the number, one less than the number of data points. Calculating that for these data, the standard deviation of the first population is 0.45, and for the second is 2.45, so clearly much more spread out. Answering some questions about this number, why do we square them? We square the deviations because, for one thing, it doesn't give us 0, so we get a meaningful number, but also the sum of squared deviations of any data set from that data set's mean is the smallest sum of squared deviations from any number. So if we went back to our data here, and we measured the average squared deviation of each of these points from, say, 7, or each of these data points from 4, we would get a bigger number than if we plug the actual mean in for that data set. That's kind of a complicated idea and hard to state in a transparent way, but what this means is that the squared deviations point to the mean in a unique way, because it gives us the smallest number when we calculate the standard deviation in this way. Another thing about the standard deviation is it has an important relationship to a class of distributions of data we'll talk about in much more detail in our next unit, and these are called normal distributions, which are also sometimes called bell curves, and they're probably on the cover of most statistics textbooks. We'll talk about those shortly. Spoiler alert, if we look at a bell curve like this, The standard deviation, here we have the mean in the center, or x bar. The standard deviation is the distance from the mean to the inflection point of that function. That's a thing we can prove. Finally, a really simple thing about why do we take the square root? Well, if I calculated the variance s squared, suppose I'm measuring heights of individuals, that number would give me height squared, and that's not really a thing we care about. We like to compare, if we're talking about heights, we like to compare heights. So by taking the square root, we get back to a number with the same units as the data itself. Now, why do we divide by n minus 1 in that formula? That formula for the standard deviation, remember, it can be called s, or we can use the lowercase Greek letter sigma. It's equal to, remember, 1 over n minus 1 times the average difference from each data point to the mean of the data set squared. I equals 1 to n, and we take the whole thing square rooted. So this number, n minus 1, is called the degrees of freedom, which you might have heard of in some physics classes, possibly even some chemistry if you did some advanced work. But because we use n numbers to calculate the mean, once we know n minus 1 of them, the final number is determined. So if we're talking about the mean already, which is a number we can calculate, we only really need n minus 1 of the data points to completely determine everything about the system. This has some more theoretical reasons that we define the standard deviation in this way, but hopefully if we're doing statistics we have a large data set and n is a big number, so the difference between using n and n minus 1 in this formula will not be very different numbers in any case. Some properties of the standard deviation. The variance computed with respect to the mean x bar, it's computed with respect to the mean, not the standard deviation. So the standard deviation and the mean, they go together like red beans and rice. We don't want to use standard deviation together with median. So if you use the median, use the 5-number summary. And if you want to report the mean, you should report the standard deviation. Remember, if the data are skewed, we want to use the median and the 5-number summary. And if the data are symmetric, then we can use x bar, the mean, and the standard deviation to summarize that data set. Also be careful that, like the mean, S is not robust. The standard deviation is not robust. And if we have a few outliers, it can really blow up the value of that standard deviation.